This video is going to be about a pretty big idea, and it's about calculus. There are only two things we can do in calculus. One of them is find the slope of a function. For example, this function f of t. Suppose at some point on the function, say this point right here, I want to know what is the slope. What is the slope? What is the slope of a tangent line to the graph that looks just like this? So we have a tool that lets us do that. It's called the derivative. And here the derivative at this point would be df dt evaluated at this value x. So there are lots of applications of that. We want to know how quickly something's moving. If f of t here represented position as a function of time, then df dt would be the velocity, the rate of change of the position with respect to time. We might also want to know where is the slope changing the fastest. I think it's somewhere in this neighborhood, probably right about here, where the slope looks like this. Here I see the slope is negative, but it's the most extreme value I see anywhere, except maybe over here, this region. A third very significant thing we might want to know about a function is where is its slope equal to 0? So for example, if this represented my profit, and this was how many computers I produce, the number of items, I'm interested in places where my profit is a maximum. So I can see right around this number of items, there's a maximum where the slope is 0. Right around here, there's a maximum. Probably I want to avoid this place right here where there's a minimum. So these three locations here, I have 0 slope. And being able to find that lets us optimize systems, whether they're economic or biological systems or industrial processes. So that's finding the slope. We call that the derivative. There's only one other thing we do in calculus, and that's this. Suppose I have some value on my t-axis here, a value called a, and some later time, I'll call that later time b, and I want to know how much area there is between a and b under that function. This is the only other thing we can do in calculus, and it's called an integral. So the integral from a to b we write as the long S for sum, because we're summing up an area, integral from a to b of f of t dt in this case. That's how we write it. So here's my claim in this video. Finding the slope and finding the area like this are the opposite operations from each other. So I'm answering, why is finding slope and finding area? Why are those opposite operations? And what do I mean by opposite? I mean one undoes the other. So for example, suppose I take a positive number and I square it. How do I undo that? The square root. Or if I take some number, take its cosine of x, how do I undo that? I take the inverse cosine, cos to the -1 of cos of x. That would just give me x. This will give me, if it's a positive number, it'll give me x. If it's positive or negative, it'll give me absolute x. So my claim is that if I find the area under a function, or I find the slope of that function, doing one of those can undo the other process. Let's see why this is the case. Suppose I've got my function f of t here. It's a function of time on my horizontal axis. And up to this time, which I will call x, we're going to consider the area under the function. And by under, I mean between the function and the t-axis. So this area, we're going to give it a name. We'll call that g of x. And notice that's a function as well. G is a function of x, where f is a function of t. So this means if I took my x here and slid it to the right, I'd be accumulating more area. So let's do that. Let's consider what would the area be if I considered not g of x, but g of x plus dx, just a little bit more than x. So this value here is going to be representative of this area, g of x plus dx. So what is the difference between g of x plus dx and g of x? Well, it's going to be this area in between the red line and the blue line. That's the difference. If I find all of the red area and then subtract off the blue area, I'm left with just this place that's roughly rectangular. And in fact, if I make dx small enough, it'll actually become rectangular in the limit that dx gets small enough. This gets rectangular enough. So I can say g of x plus dx minus g of x is equal to that rectangle. And what's the height of that rectangle? Well, this value right here is f of x. So that's the height, and the width here is dx. So if we rearrange this and divide both sides by dx, divide by dx here, divide by dx, these cancel, and I can see that f of x has some relationship to g of x. It's g of x plus a little bit minus g of x over that little bit. And I know if I throw a limit on here, dx goes to 0. That's just the derivative of g of x. So what does this mean? It means that the derivative of the function that represents the area is the function itself, the function f itself. So that function g that represents the area, if I take its derivative, I get the function f itself. So that means I can undo finding an area by finding a slope. And I can undo finding a slope, or a function that is the mapping of all the slopes here, by finding the function that describes the area from 0 up to any given value of f. This idea has a name. It's called the fundamental theorem of calculus.